Rex Inman had a dream. He wanted to provide more opportunities for students at the University of Oklahoma. OU was building relationships with researchers at the National Oceanic and Atmospheric Administration, establishing a precedent for government-university collaboration. The Cooperative Institute for Mesoscale Meteorological Studies was established in 1978. CIMMS research contributes to the NOAA mission through improvement of the observation, analysis, understanding, and prediction of weather elements and systems, and climate anomalies ranging in size from cloud nuclei to multi-state areas. CIMMS is one of 16 cooperative institutes within NOAA to promote collaboration between government and academics. Collaboration on research and projects furthers NOAA's mission to save lives, property, and minimize economic impact. Located at the National Weather Center, CIMMS is the largest and second oldest research organization at OU. Additionally, CIMMS has researchers outside of Oklahoma, including Missouri, Colorado, and Tennessee. As a center of excellence for more than 40 years, CIMMS scientists conduct research aimed at improving forecasts and forecasting tools used by NOAA. CIMMS research focuses on weather radar, storm scale and mesoscale modeling, improving forecasts, societal applications, and extreme weather events. Cooperative Institute's research will lead to more valuable weather and water information to support improved decisions that can reduce loss of life, injury, and damage to the economy. For more information, visit cimms.ou.edu.
I'm joined today by Chris Jewett and Lori Schultz, also a couple of the developers for this product. So we're here on hand to answer any questions you guys might have. With that, we'll go ahead and get started. The motivation behind building this product, we actually have quite a few studies that go into the making of this. We are actually still in study mode trying to improve it in many ways. The main emphasis behind this particular figure is to show that with satellite, you can see the cloud before you can actually see any echoes from radar. So if you can detect growth, then you can actually get a longer lead time on what might become mature convection in the near future. This is just another illustration, very similar idea. The present at the top right, you can see kind of a maturing thunderstorm, but 30 minutes before that and even 15 minutes before that, you can see cloud growth, and we can detect that from satellite in many instances. We've had up to 1.5 to even 2 hours lead time in some cases using this type of a method. By CI, with our lead time, we define that from the moment we do the forecast up until the first instance of CI, which is greater than or equal to 35 dB echo at minus 10 C or at base. It just depends on how we do go with it. So brief algorithm summary, we download the GOES data. We simultaneously make a convective cloud mask and produce atmospheric motion vectors, both of which go into our tracking of what we call cloud objects from T1, which is time 1. That's the prior satellite image, in time 2, T2, which is the most recent GOES image that we've received. Once we do that, we're able to run a series of temporal, spectral and temporal differencing tests called interest fields. We use those to evaluate which cloud objects are most likely growing at a rate that will produce convective initiation in the near-term future. Another example, this is actually from our display in the hazardous weather test bed in 2010 over the north shore of Lake Pontchartrain in the New Orleans area. Notice that at the top right, you have a radar image, 1744 UTC. At about that same time, we received imagery from the GOES satellite and ran it through the algorithm. We have a positive CI forecast right along the north shore, and also in the subsequent imagery that we received at 1815 UTC, you see more convection being flagged for forecasting at 1815 UTC. The first instance of 35 dB or greater echo was detected at 1832 UTC. So actually had a pretty good lead time on the first instance of most of that. Another example, this is from actually June of this year. The northern Florida, southern Georgia area, we have several positive CI forecasts. The first image at the bottom left is the radar imagery showing no echoes being detected, but from satellite we do see clouds that are growing. All the red objects are the positive CI forecast, and you can see the corresponding yellow rings in the subsequent radar imagery showing that these forecasts did verify. There was a miss. If you look in the top left pane, the blue object, the null object, never received a positive CI forecast yet at the 1717 UTC see we had our image. Actually, there was a storm. So obviously, we still have a long way to go. This is an example just illustrating one of the instances where we had a miss. So just a rundown of the product. Again, we do run it day and night. The night needs a lot of work right now. We are able to ingest a lot of rapid scan data, all of it actually. We do parallax correct the data to try to ensure that it's the objects in the forecast are spatially correct over any domain. The runtime from the moment that we receive our satellite data is about 1.5 minutes until we receive output at night, and about 2.5 minutes during the day. Average lead time of about 30 minutes. And we have seen satellite forecasts verify up to 2 hours in the future. There are some known limitations we run into. For example, the first one is cirrus contamination. There are 2 issues with it. First of all, we don't process anything under cirrus contaminated scenes. The spectral signature is either distorted or we just simply can't see the low-level pre-CEI or immature convective clouds. The other issue is what we call false vertical growth. Let's say that at time 1 you have a low-level cumulus cloud. It's not covered by cirrus, but by time 2, 15 to 30 minutes later, some high-level cirrus has intercepted the scene between the cloud and the satellite. It makes the brightness temperatures drop. It actually triggers most of the temporal interest fields, and it makes it look like the cloud top is growing significantly. So this leads to false alarms. Even though the cloud is really not grown,